basis for GenAI workloads. And we have Dr. Priyanka Naik here. So I'd just like to give a brief bio about her. Priyanka Naik is a research scientist at IBM India Research Lab and is part of GenAI platform team. Priyanka's prior research explored the space of cloud deployment, networking, and observability of microservices such as network functions and extending the same for multi-cloud deployments. Prior to joining IBM, she received her PhD from IIT Bombay, India. She has been a speaker for multiple tutorials and a co-author to a cloud network book. So over to you, ma'am.
Thanks for the introduction. They say for Gen AI or any AI workload, right? So how the GPU itself has over the years for it to be Gen AI ready, and what are the challenges still in place which we as researchers can work on to improve it further, right? So by default, when GPUs were started, they were built majorly for graphics, right? They were built as part of the graphics pipeline, right? And what typically was there, the architecture that these graphic cards followed was something that they mirrored the software architecture that was required by these graphics pipeline. And this was challenging from a hardware perspective because every time there was a software upgrade, it required reconfiguring this pipeline itself. Like you can see, there are fragment shaders, there are vertex shaders, and there was no concrete unit that could be identified for these architectures. And that's where companies like NVIDIA introduced something what is called as a streaming multiprocessor or a SM, which was the single smallest block of unit or block of processor which could be put in the GPUs and could be replicated, or multiple of these could be formed on the die, or it could be built on a die for these chips, right? And these comprise are similar to what we've been seeing traditionally for our CPU processors. They had cores, they had a cache, they had a shared memory, and they had something special, what is called as empty issue. What it did was, what it expects as part of the multiprocessor is all the cores of the processors to be executing the same kind of processing. And they try to diverge, the empty issue raises an error and it tries to align them back. Right, so this kind of architecture was followed by NVIDIA, and this kind of dice were adopted. Right, and this was a move first from being a graphics card to something that's more standardized. And this introduced, because there were multiple cores, there were some more concepts that were introduced as part of programming, as well as how the device was, as you said, as we saw, the SMs were there. So how you program these SMs also changed. Right? So traditionally we've been used to spawn multiple threads for running multi-threaded application, or want to scale any application, right? So that was good when you were running your applications on a CPU processor. But with multiple cores in your SMs, you could actually run multiple threads parallelly. And to categorize them better, or to analyze them better, or identify the issues better, they were grouped into what was called as a thread block. That is, you can identify thread block as multiple threads doing the same kind of job, right? And one thread block can comprise of multiple warps, and one warp can be mapped to, say, 32 threads, which traditionally we are known of running. So one warp is 32 threads. Thread block could run multiple warps. And the SM's performance depend on how many thread blocks it could run at the moment, right? And as we said earlier, it was empty issue's job to see that within a warp, a thread may not diverge from other threads' execution. Right? So this was what streaming multiprocessor and warp architecture that was followed. Right? So this is good for us as a hardware perspective, which we want to move away from the graphics processing. And when we started moving or started using these GPUs, not just for graphics, but for other computations, especially in AI workloads, there was a need to introduce some APIs for say the most common operation that's being done in AI, that is matrix operation. So there were APIs exposed by CUDA to say do your operations which were optimized to do load, accumulate, and store operations for these matrix. And these were optimized, and there was an optimization that was done on the software part. And on the hardware part, these tensors these cores were also optimized in terms of how they were doing these operations at the hardware level. And these cores were then called as tensor cores. So you can consider tensor core as the first kind of core at the hardware level, which is optimized to do AI kind of computations. Right? So this is how the GPUs kept evolving themselves to be ready for AI workloads. And with over the years, these architecture or these dies started reducing in sizes. There were more cores to be added, and NVIDIA has so there was A series, which was Ampere. There's L series. There was Hopper H series. We keep referring to them over the slides. And then the latest one is Blackwell, which was a 3 processor die, which was introduced. Right, so this is how GPUs evolved. Then came the wave of generative AI, which was not just normal ML AI workloads, but used something called as transformers to do. Transformers were used in their training stack. So to understand this generative AI architecture better, let's go over some basic background. So the first step in any generative AI architecture is data preparation. Right? So this involves pre-trained data. That is the data that is used by these generative AI workloads or generative AI training is collected from public or private resources and requires some detoxification or deduplication or removal. Right? And it also needs to be aligned to specific stars and might require some human annotation or some labeling. Right? So that's where the data is prepared to be given to the models. The second stage is data pre-training and training, where you decide how the model that you want to run. So you decide how you want to parallelize it, how the data needs to be split across these parallel when it's parallelized, and we dive into a bit detail on how these are parallelized, and you will see how you create the data for you align the data for these parallel sets, right? And when you train them. Once it is trained, the third step is alignment, right? So the model that you train runs on multiple days or sometimes weeks, right? And these are called as base models that get built. And it might happen that you require these models for some specific use cases that say some industry application or say your home automation system, right? So you require some special data to be inputted for these specific use cases. And there are two ways to go about it, where first is you can change the model parameters by a technique called as fine-tuning. That is, you give some specific inputs to this model, and it's really trained on these models, on these parameters again. But which is not feasible every time based on resource constraints and some other challenges. The other technique that's being used widely right now is prompt engineering. It is based on the inputs that you give as you're using the system or as you're using the model updates its parameters on the code. That is, you don't require to update your model parameters per se, right? And this is good, and because you don't have to change the model parameters and retrain it every time. The next task is once you have a fine-tuned model or a model ready for you to be used, you have to evaluate for certain metrics. It need not be just the accuracy of how much efficiently it performs or how much efficiently it answers your question and chat tools like our common use tool like ChatGPT, but other things, that is how fair it is, how it reduces toxicity, and how better it utilizes the resources from a systems perspective, right? Now that these things are there in place, you've trained the model, you fine-tuned the model, you deploy them, right? So you deploy them on cloud. So there are certain challenges because once you go on a shared infrastructure, resource constraints start popping in, and then there are optimizations done from the model point of view of how you can get the same accuracy with reduced number of resources by using quantization, or you can better manage your memory. Right? So this is where majorly as a system researcher or a system person, you can use your skills or use your handle some challenges and provide some solutions. So we'll dig into, as major part of our talk today, we'll deep dive into what more we can do from the deployment point of view, right? So there are majorly 5 things that need our attention. So these are the things where there are challenges still open, and as a system researcher, we can focus on, and we go over them today. So the first one is this is something that was not majorly seen in other prior AI workloads like RNN and CNNs, but majorly seen in today's Gen AI workloads with which use transformers, is that the memory becomes a bottleneck. Right, so why it becomes a bottleneck? Let's go back on a bit of background on that. So most of the chips that are there in GPUs today have a high bandwidth memory as part of their on the chip memory, which is say 40 GBs for 800s or 80 GBs for H100s. But this memory is not enough, so it has to use, say, it has to context switch or get the data, get the memory, use a shared memory that is provided as part of the CPU, like your normal processors. But there are other memories that are these memories itself are split into what are called as global memories and constant memories that are there on this device, right? And there is a lot of copy that needs to happen when say one GPU needs to talk to other GPU on the same node itself, right? And you can see, as you can see in this figure that not all, like your registers are not shared. There's only the global memory that gets shared across these nodes, and because of these, a lot of overhead comes when you have a large model which has to be split across multiple GPUs, and there are a lot of memory overhead or memory copies that happen that reduce the performance or delay the whole training or fine-tuning time itself. Right? So there are a lot of optimizations that have been introduced, like say you have a unified virtual addressing space, so you don't have to explicitly specify, say, I need to transfer this data from host to device or device to host. You can have a shared unified addressing, so you can directly, using pointers, get the data across hosts and GPUs directly. And there is something that's new in new versions of the NVIDIA GPUs like H100, which is called as a tensor memory accelerator. That is, a large block of transfer is possible because these global memories have the memory access have been accelerated, and they enable large block of data that can be transferred across these nodes to improve the data sharing capability or memory sharing capability amongst these GPUs, right? And to synchronize these communications itself, there is a new technique called as asynchronous transaction barrier introduced, which allows the CUDA threads which are on these GPUs, running on these GPUs to synchronize these threads properly. These barriers can be introduced. That is, you can consider these as peaky threads. When you use a peaky thread, you wait for the join to execute, that is, wait for all the 3 threads to come back. You can consider this as a similar technique where you wait for these threads to come back, and it can be considered as a barrier. That is, you wait for the barrier to complete. Right, so these are kind of techniques that are used to improve how the memory is managed. But as you can see, there are still challenges on how I can say that there are still, they've improved a lot on how the memory bottlenecks can be reduced, but there are still challenges when you come to training, where there are a lot of memory transfers still happening across GPUs. Right? So now we spoke about memory. next that we can talk about as a system point of view is the compute, right? So the GPU is something that is a very costly resource for us right now. So you need to efficiently utilize these GPUs. That is, there should not be any GPU cycles that are getting waste or GPU time that is not being efficiently utilized. Right? So there are techniques that are used for efficient GPU compute management. That is, you can share these GPUs efficiently across multiple users and multiple applications for efficient utilization of these GPUs. So the first technique that's used is called as time slicing. That is, you divide the GPU resources into time intervals. So sharing and provides fair utilization across applications that want to use the GPU resource. But as you can see, there is time slicing being used, so there is no clear, complete isolation that's provided using time slicing. Right? And when this demand or need for time slicing comes into picture, when you have multiple users using these GPU that are available, and this is a case, this is a classic case, this is a common case that happens in all data centers today. Something that's coming from the hardware perspective is what is called, or is provided from the hardware, is something what is called as multi-instance GPU or MIG. Right? What it provides is isolated GPU instances for each of your users. So there is a clear isolation on the resources that are being provided. It is the compute as well as the memory can be isolated for these GPU instances. So, and the other good feature of this MIG is it provides dynamic partitioning. What we mean by that is an administrator can dynamically adjust the number and size of MIG instances to adapt to the changing workloads. Right? So this is a good feature that the hardwares, which are very recent hardware, edge generates have introduced in the market today. Right? So this, as any GPU sharing technique, provides good optimized resource utilization. But there can be cases where, because there's a very recent technology, there can be cases where you don't have MIG in your GPUs, then there is something that's widely used right now is multi-process service or MPS. That is, you share a single GPU among efficiently share a single GPU among CUDA applications by what is called as CUDA context. That is, multiple CUDA contexts share these single GPU, and there is a seamless context switching that happens across these CUDA contexts. Right? And because there is context switch happening, there is a challenge that it is not complete isolation that MIG provides, but it is quite good when you want to maximize your throughput. Right? So there are a lot of work in this space, as like one of the work that IBM is working on is InstaSlice, where it is trying to provide this kind of isolation kind of environment over these solutions like MPS, for GPUs where you don't have MIG support. Right? So the space is also quite open on how you can provide techniques on efficient GPU sharing for optimizing the GPU utilization. The next thing that we would go into with more detail is, now we said that you want to optimize your memory, you want to optimize how your compute is being used. Right? And the compute, another challenge for using the compute well is you want to run large models on these GPUs, right? And you cannot just use a single GPU every time. It will take you months to get the training done. So you have to use multiple GPUs to get your training done faster, right? But this cannot be just done out of the box. You have to split your models or split this compute in an efficient way. That is, parallelize this compute in an efficient way so that you can use your compute better and you can reduce your job make span, that is, the total time it takes to train a data or train or complete a job, to reduce that, right? So there are multiple techniques in market today where how you can efficiently use this compute by parallelizing these your models or your data, right? So the first technique that's being commonly used by all models today is data parallel. That is, you shard your data across the multiple GPUs that are being used. And at the end of, say, one cycle or one layer, you just share your minimum, as we say, gradients that need to be shared across these multiple GPUs, right? So think it that way. That is, this is some example that I picked up from Hugging Face example itself. That is, if you're going on a trek, you have an axe, you have a tent, you have a stove, and three of you are going on a trek. You split across your, like, one carries a tent, one carries the kettle, and then you just share your resources, right? That's how you split your data across these GPUs. The second kind of parallelization technique is model parallelization. What we mean by model parallelization, so a brief step back and how transformers models are, that is, they work in multiple layers, or any algorithm or AI algorithms have multiple layers in which they run, right? So what do you mean by model parallel is you split vertically across this layer. So suppose you have, for example, 8 layers, you say 1 to 4 will run on GPU 1 and 1 to 4 will run on GPU 1 and 5 to 8 will run on GPU 2, right? So that's how you split vertically across your GPUs. But as you can see, these layers need to talk to each other. So it's good when these layers are running on the same GPU. That is, 1 to 2 can talk to each other, 2 to 3 can talk to each other on the same GPU itself. But as you can see, for the 4th and the 5th layer, it has to be across GPU communication, and this is not quite efficient because if your networking is not quite optimized, it can add to additional latency, more latency compared to internal GPU communication, right? And similarly, there is a dependency, right? So 8th layer needs to complete and talk back to your GPU 0 for it to run the next epoch or next batch of data that it needs to process, right? So it bottlenecked by how efficient your network is, but it's also bottlenecked by not bottlenecked by you lose on the compute. That is, you leave your GPU idle for a long time because you're waiting for the 8th layer to complete your processing to come back to start your GPU layer 1 processing again. Right? So the GPU 1 on which these was running, it's actually idle for some time. So how do you improve these or how to reduce this idle cycles is what is called improved using a technique called as pipeline parallelization, where the batches in which the data is being processed is all split into what is called as micro batches, and you pipeline these micro batches. So what happens is, by the time one micro batch is being executed, the other micro batch is complete, so the other layer can start running on this micro batch. So the wait cycle is reduced and the bubbles that it form are reduced. Bubble in the sense the wait time or the idle bubble that is there for the GPU is reduced. Right? So this is how you can improve the GPU utilization using pipeline parallelization technique. But all these things have a challenge on how efficiently you decide what kind of split you want to do for your data, or what batch size you want to use, what kind of micro batch size you want to use. So these are not the hyperparameters that these algorithms keep on tuning, but these are system layer optimizations or system layers configurations that need to be done to efficiently use these GPUs and efficiently reduce the job completion time for your GenAI workloads. Right? So we are working on a simulation or a simulator which will help simulate these parallelization techniques for your models based on your batch sizes or other configurations, and can predict that, okay, if you use this batch size, you'll get so and so training time, or you can reduce it by so and X or Y amount. Right? And what we are trying to do with this simulator as well is, if you want to introduce, say, a combination of these parallelization techniques, that is, you want to fuse multiple of these parallelization techniques, you can check of what kind of efficiency you will get, or is there really an improvement of fusing these techniques for your kind of data or your kind of model. Right? So this is one part of things that we are working at IBM. The next, now we spoke about the compute, we spoke about the memory. Third thing that will come into place, or third thing in which things have been optimized, is how efficiently you handle networking for your GPU workloads or GenAI. Right, so there are a lot of optimizations that have happened over the years, where earlier, by default, whatever communication needs to be happening across GPUs or between GPU to host, there used to be multiple memory copies, right? So to reduce all these copies, there were techniques done or techniques introduced. The first one was you have a common memory region for GPUs and NICs on a host so that they can talk to each other without the CPU intervention on the data. The second was GPU Direct 2, where there was a peer-to-peer communication across the GPUs directly over PCI without the involvement of the host. Right? The third technique was the direct memory access across GPUs, not on one node but across nodes, where there would be a common memory. You can directly use point techniques, similar to the normal RDMA techniques that you would have heard of. Right? So, and the next technique was, okay, you are transferring the data, but there might be situations where there is a async or a blocking, non-blocking thing required, and there are async communication protocols or primitives introduced for communication across nodes via the NIC that's required, right? So, async communication between the GPU and the NIC was introduced to reduce the control path overheads. The last is something what is introduced as part of data center on chip architecture, where you reduce the overheads of communication between the GPU and NIC of your device, so that faster communications can happen across GPUs, across multiple nodes. Right? And these were techniques that were used from a programming point of view, from a CUDA point of view. What optimizations were done from hardware point of view was introduction of techniques like NVLinks, which involved direct peer-to-peer communications across GPUs for optimizing their communications. But then it was seen that just having peer-to-peer communications won't always help, because it would require you to have a peer-to-peer communication with each of the GPUs, which is not always visible, and that's where NV switches were introduced, which helped communication across multiple GPUs, right? But as you can see, over the years, these could not reach the performances that were required across these. There were not high optimizations done. They just tripled or doubled the number of links that were there across these switches, but they did not actually use some technology or some smart techniques to improve these performance with the existing architecture itself. Right? So they could reach around 450 Gbps with the latest H100s in NVIDIA. Right, so this typically, if you take some papers from Meta, you can see that for the Llama modeling training itself, what the architecture they use is for communication within a node. They use, say, NVLink or NVSwitch, but across nodes communication, they use something called as InfiniBand. Right, and InfiniBand is something that's not always visible because it's quite expensive. So what is being used right now is your Ethernet is being optimized to support these cross-node communication for these GPUs that are running across nodes. And there are a lot of improvements in terms of how much they can scale. That is, by 2025, it's expected to reach around 102 Gbps speed up of the Ethernet that it can support. And it's good because the Ethernet provides a lot of things on how the protocol is supported or how traditionally it has supported our communication. So it's good if your Ethernet itself can be used for these GPU communications. Right, so this was all the background on all the resources that are being used for these communications. Right, but once these optimizations are there in place, the other challenge that comes into picture in terms of deployment is what platform you can support for easy deployment of these applications on, say, your data centers or on your clouds. Right, so there are a lot of platforms that were there traditionally for your HPC workloads, like, say, LSF, or Slurm or PPS that were being used for heterogeneous or HPC job scheduling and resource management was handled by these platforms. But and of course, something that's being used today widely for your microservices like Kubernetes, right? But there needs to be a rethink on how these platforms are being used for GenAI workload in terms of how they support, say, efficient GPU sharing. The supports that are there or being provided by your hardware, say, new GPUs, are they efficiently being used? Can be efficiently supported by your Kubernetes environment? All these need to be reworked, or if not, have to be enabled. Right? And they have to scale. See, there are new challenges that have come up on how memory becomes a bottleneck, or how you want to parallelize or scale up or down these usage of GPUs. Right? You cannot. There can be some IO that you're waiting for, and your application is using the GPUs for this long amount of time, and that's not efficient utilization of your GPUs. So how well you efficiently use these GPUs and scale up and scale down your workloads that are running on your platforms today or running on your clouds today becomes very critical, right? So we are trying to introduce a workload manager which will work across these underlying solutions that were being traditionally used for workload management, but will support some Gen AI aware parallelization techniques where it will take care that, okay, training is going on, there will be eval that will come on later, so how we can efficiently schedule these two jobs. These are heterogeneous jobs in the Gen AI pipeline itself, how you can efficiently schedule these jobs together so that you can reduce the total time of training to be complete, because it involves eval to be completed seamlessly as well. Right? And how you can say scale up and scale down. Say you need vertical scaling for your training job, but because there are some workloads like inferencing where you can have multiple replicas, can you scale them horizontally as well? So that kind of decisions across these workload types needs to be taken, and this is what our workload manager would provide, and this is what we are actively working on at IBM. So before stopping my talk today, I'll just leave out on if you want to kickstart, because this is the year, last year was something that we moved from traditional systems for our microservice kind of applications to how you can provide system optimizations for your workloads. And if you want to get started on your journey as well, these are some links or these are some papers that you can start off to learn more about these challenges that are there in this space. So, thank you.
Thanks for the wonderful talk. Yeah, so time for the questions. So I have one question now. Like in your one of your background slides,
Okay.
I don't remember the slide number, but we're talking about time slicing and some.
Your voice is not clear, Krishna.
Okay, just.
Which slide can you point me to?
I think it's, yeah, this one. Am I audible now?
Yeah.
Yeah. So, I was just wondering the difference between the time slicing and the MPS. Could you explain a bit on it so that I understand? Like I need to say that both seem to be similar to me in some way.
Yeah. In a way, yes, but it depends on how CUDA supports it. So MBA time slicing, it's like your GPU is being split into slices, but here for NBS you have something called as CUDA context that is being used for sharing across these multiple applications.
Is it like they are shared across in terms of time intervals? Is that what happens?
Yes, you can assume in terms of there it can be some, say, milliseconds, here it can be nanoseconds, because there is fast context switches that can happen when you use it.
So, any more doubts? Okay, so let's start the speaker again.
Thank you. And with that note, I just have to announce that we are opening our hirings in this space. So in case if any one of you are interested, do write to me. Thank you. Do reach out. Thanks.